Hello, geometry students. Mr. Zacek back better than ever. We are going to be talking about circles and arcs here in lesson 6 of unit 10. And so some of this is just going to be review here at the beginning, and then we're going to get into some more specific vocabulary terms as we go. So if we have a plane, a circle is the set of all points equidistant from a given point called the center, and that's what we call a circle. The diameter is the segment that contains the center of the circle and has both endpoints on the circle. So, a diameter contains the center and it has endpoints on the circle. That's something we should be familiar with. A radius has one endpoint at the center and the other endpoint on the circle. So anything like that is a radius. So if congruent circles have congruent radii, so if two circles have the same length radius, then those two circles are congruent. All right, all that stuff we're very familiar with. Here's where we begin to get a little bit new information. A central angle is an angle whose vertex is at the center of the circle. So if we look at this angle here in this picture, P is the center of the circle, and angle APC is a central angle. PC is the radius, and AB is the diameter. So over here, this picture, angle APB is a central angle, again, because the vertex of the angle is the center. That's what makes it. So the vertex is the center of the circle. That's the key. Then we have arc, and arc is a part of a circle. So a semicircle is half the circle. A minor arc is smaller than a semicircle. So this is going to be, if we think about some degrees, this is going to be 180 degrees. A minor arc would be less than 180, and a major arc would be more than 180. So in this picture here, RS is the minor arc. You can see it's less than half the circle. And then STR is the major arc. And when we have a major arc, we're going to use 3 points, and a minor arc, we just use the 2 points. So minor arcs are named by the endpoints, like we see over here, RS, that's the minor arc. And major arcs are named by the endpoints and another point on the arc. So in this, again, STR is the major arc, RS is the minor arc. So the measure of the minor arc is equal to the measure of its corresponding central angle. So as we look at this picture, we've got the angle here and the arc are the same. So they're both 50 degrees. Central angle equals the intercepted arc. So the measure of a major arc is equal to the measure of the related minor arc are subtracted from 360. So in this diagram over here, since we've got that arc is 350, the other arc here would be 310 degrees. So the two of them together have to add up to 360. All right, and then some other kind of things that you would assume make sense. Adjacent arcs are arcs of the same circle that have exactly one endpoint in common. So AB and BC. And so we have the arc addition postulate, which means the measure of this entire arc here is equal to the smaller arc, the two adjacent arcs added together. So nothing really complex there, just, things that make sense. We can find the length of a part of a circle's circumference by relating it to an angle in a circle. And we will set up a proportion because the length of an arc is part of the circumference. So here's the proportion. The length of the arc divided by the circumference equals the central angle divided by 360. All right, so we're going to use this for our arc length. We'll do some examples with that later on. The length of the arc, it's a fraction of the total, right? So you think of this, the top is the part, the bottom is the whole. The circumference is the whole distance. The central angle is the part, 360 is the whole. So when we're looking about circles, many properties of circles deal with ratios that stay the same because all circles are similar to each other. So all circles are similar to each other. Why? Because there's a translation that maps circle O so that it shares the same center. And if it shares the same center, then what we can do is we can dilate it with the scale factor of HK. Remember from our dilation conversation that it's always the image over the pre-image. So the image to H divided by K. So a translation followed by a dilation is a similarity transformation. Therefore, the circles are similar. And then the last one is coplanar circles that have the same center are called concentric circles. So you see that anytime if you were to draw another one and it has the same center, that's a very poorly drawn circle, but that is also true. So the diagram at the right shows two circles with the same center. It's already been shown that concentric circles are similar under a dilation transformation. And so the scale factor of the smaller circle to the larger circle is the radius of the smaller one divided by the radius of the larger one. So we want to think similar, you should think proportional. Similarity means that things are proportional to each other. So we have a ratio. And so what happens is, just to kind of summarize this, is that the ratio of the radiuses, the radii, is the same ratio as the arc lengths because they're similar. So we can set up a proportion. So the ratio of the arc length to the radius will always yield the same constant ratio. And what that's going to do is allow us just to solve some of these different problems. All right, so let's put all of that information into an application as we do this here. Okay, what are the minor arcs of circle O? Well, one of them would be AC, one of them would be CE, one of them would be DE, and one of them would be AD. Again, a minor arc is one that is less than half the circle. So what are the semicircles? Well, the way you find the semicircles is through the diameters. So DAC, that would be a semicircle. And then the other side of that would be CED. And then the other one here would be ACE. So that arc starting at A, going through point C, ending at E. And then on the flip side of that would be ADE. That would be the other half of the circle. Okay, so what are the major arcs that contain point A? Now a major arc has to be bigger than a semicircle. So we could do, like, if we started at EAC, that would be a major arc. We could do CDA, start at C, come around, go through D up to A. What else? We could do AED. All right, start at A, go through E, end at D. So we got a bunch. There might be more, but I think you get the idea of what are the major arcs that we have. So when you're looking at a question here now in 2 where you have this a diagram, let's understand what we have. We have a center and we have this arc here, 58 degrees. Well, we should get this idea that that angle is also going to be 58 degrees. And because this angle here, BOC, is 32, that means arc BC would also be 32. So that would be 32 degrees. And the reason is it equals the central angle. And then it asks for arc BD, the measure of arc BD. Well, that's the measure of arc BC plus the measure of arc CD. We're going to add those two together, which would be 32 plus 58. So the measure of arc BD would equal 90 degrees. And then we've got the measure of ABC. Well, what is ABC? So ABC, well, look at that. That's a semicircle. So what do we know the measure of a semicircle is? That's 180 degrees. And then we've got the measure of arc AB. Well, AB would equal 180 minus the measure of arc BC. So that would be 180 minus 32, which would be 148 degrees. Okay, so we're just kind of, this arc here is 148. And then if you wanted to find the arc AD or DA, that would be 180 minus 58, which would be 122. So that's this arc here. Again, that angle would be 122. This angle would be 148. So we got half a circle is 180, all the way around is 360. Central angles equal the intercepted arcs. Those are the two concepts that we're working with there. All right, so a car has a circular turning radius of 16.1 feet. The distance between the two front tires is 4.7 feet. How much further does a tire on the outside of the turn travel than the tire on the inside? Round your answer to the nearest tenth of a foot. Okay, so what we're looking at here is the circumference. Cherry is delicious pie. Well, the outside, so the difference is going to equal the difference in the circumferences. So this would be the larger diameter, which is going to be, let's figure out the radius first of the larger circle. So the larger circle, 16.1 plus 4.7 is going to be 20.8. Now here's where people get tricked. So the large radius is 20.8. That means the large diameter would be 41.6. So the small radius, or the inside one, which is 16.1, has a diameter of 32.2. So we're taking the difference in the circumference, which would be 41.6 pi minus 32.2 pi. And we might, forget that we have to find the diameter in that case. So it's going to be, come on. So push too many times. 41.6 pi minus, what was it, 32.2 pi, which is 29.531. So the difference would be 29.531 to the nearest tenth of a foot. So that tire is going to be 29.5 feet. So this is one of the reasons why they recommend that you rotate your tires, because when you're turning, the wheel ends up getting more wear. Different tires get more wear. Sometimes that happens for other reasons, but this would be a problem for NASCAR drivers because they're always going in the same direction. So their outside tires are always getting more wear than the inside tires because they're just going to spin more. Okay. So what is the length of arc XY? Express your answer in terms of pi. So again, XY here is a part of this, and so what we want to think about now is we got to find the circumference. So the diameter is 16, the radius is 8, so the circumference equals the diameter times pi, which is 16 pi. So our arc length, xy, which I'm just going to use the variable x here. I'm going to do x over 16 pi equals, now we see this angle here, this is a 90-degree angle, 90 over 360. Okay, that's our formula from earlier. So what do we have? Arc length over circumference equals central angle over 360. And so now we can just go ahead and use our cross product property. 360x equals, what's 90 times 16? So 90 times 16 is 1440. Okay, so 1440 pi. And then we're going to divide that by 360. We're going to leave it in terms of pi, so I'm not putting the pi in the calculator. And that comes out to be 4. So when we divide that by 360, it would be 4 pi. Okay, so the length of xy equals 4 pi inches. Okay, so let's try this again here. What is the length of arc xpy? So again, here's our central angle, so it's going to be, and we've got a radius of 15. That means our diameter is going to be 30, and our circumference is d pi. So the arc length, I'm going to call this x again, we're trying to find, divided by the circumference, which would be 30 pi, is 240 over 360. So we cross multiply, 360x equals 240 times 30. So 240 times 30. We're going to divide that by 360. It's going to be 20 pi. Okay, so 20 pi. I forgot what that came out to be. 7,200. Okay, so 7,200 pi. Divide by 360. When you divide by 360, you get 20 pi, so, which is the measure of our arc. So how might we apply that? A sprinkler head is equidistant from flower garden A and small shrub B. The sprinkler waters in a circular pattern. If the length of minor arc AB is 12 feet, so we got 12 feet here, and the radius of the circle is 10 feet, find the measure of the central angle subtended by the minor arc AB. Okay, so how much is this sprinkler moving? Well, the radius is 10, that means the diameter would be 20. In this case, we know the arc length. So the arc length divided by the circumference equals the angle divided by 360. So now what we're finding is the angle. So it's going to be 20 pi x equals 12 times 360. So what is 12 times 360? 12 times 360, 4,320. 4,320. Then we're going to divide that by 20 pi. So put the fraction template in, and we'll divide by 20 pi, and that's 68.8 to the nearest degree would be approximately 69 degrees. Okay, so the sprinkler head has a radius of 16, or angle of 69 degrees that it's moving. Okay, so in the diagram below, circle 1 has a radius of 4, while circle 2 has a radius of 6.5, and angle A intercepts an arc length of pi, and angle B intercepts an arc length of 13 pi over 8. Dominic thinks that angle B and angle A and angle B have the same radian measure. State whether Dominic is correct or not. Explain why. Okay, so we could use the proportions to do this, or if you'll recall from last lesson, we we talked about a formula, S equals R theta. Okay, so S is the arc length, and this is in radians, equals the radius times the central angle. Okay, and the key is that this is in radians. All right, so angle A and angle B then. So S is pi equals 4 times A. All right, so if we're going to solve that for A, we would just divide by 4. So pi over 4 equals A in this one. Now over here, our S is 13 pi over 8 equals 6.5 times B. So we got to divide that by 6.5. All right, so let's see what happens when we divide 13 pi over 8 by 6.5. So put in our fraction template, 13 pi over 8 divided by 6.5, okay, comes out to that number. Now, the other one was 4 divided by pi, and so that's 1 point, or was it the other way around? Hang on. Pi divided by 4, excuse me. Okay, so let's try that. So pi divided by 4, 0.7853. What was the other one? 0.7853. So what do we notice? Well, they're actually the same. Okay, so this is 0.7853 equals A, 0.7853 equals B. Okay, Dominic thinks that angles A and angle B have the same radian measure. And so, yes, Dominic is correct. Because both angles are 0.7853 radians. All right, so we use S equals R theta. So that S equals R theta, again, that is something that we can only use when we have a radian measure for the central angle. Otherwise, we're using the proportion that we had before. Okay, we're going to introduce a similar concept next time in lesson 7 for the area of a sector. All right, I'll see you back here soon.